Right, so in this lecture I'm going to review some basic concepts that lead up to the t-test and the linear model. I'm going to open up my slides first. So these slides are going to be available to you over Moodle. You will also have the source code that's behind these slides, so you can rerun all the code yourself. But right now my goal is to walk you through the materials that are covered here. Okay, so we're going to first start by reviewing some basic ideas that you may or may not have covered in the winter course. So this is the idea of a random variable, and what I want you to think about here is this very intuitive concept of thinking about what happens if you're doing an experiment like this, right? So suppose I'm doing an experiment where I'm tossing a coin, and so let's say I'm tossing a coin until I get a heads. That's my goal. I will stop counting the number of times I toss a coin as soon as I get a heads. So what could happen is that I toss the coin once and I get a heads immediately. So that is one coin toss that I have done, right? That gave me a heads. But it may happen that if I do the experiment, I may have to toss the coin twice until I get a heads, right? So what I'm doing here is that I am doing an experiment each time, this time and this time here, and I'm recording the number of times I have to toss a coin till I get a heads, right? So, and you can imagine now that the number of possibilities could be 3, 4, all the way to infinity, although some large number like 100 or something larger is very unlikely, because I'm likely to get a heads pretty soon if I'm tossing coins, right? So really what's happening here is that these possibilities, heads, tails, heads, all these possibilities, these are actually our sample space in the experiment. These are the possible outcomes you can have, and you can have different probabilities associated with each outcome. This could have some probability P1, this could have a probability P2, right? So you could get a heads in the second toss with some probability P2, right? So there's a probability associated with each possible outcome, and each possible outcome is like heads, tails, heads, tails, heads, and so on. And each of these possible outcomes is being mapped onto some numerical value, which is the number of coin tosses that we did till we got a heads. Okay, so this actually leads us to the concept of formalizing the concept of a random variable, and the basic concept works like this. So we're going to assume that the underlying machinery that's generating this data, this possible set of outcomes, here, right? The underlying machinery is being generated from a function called a random variable, which associates with every possible outcome omega that is in the set of x. So this is every possible outcome that I'm talking about here, associates with every possible outcome some number, right? So if you remember, that's what I just did here. For every one of these possible outcomes, I had a number 1, 2, 3, etc. as a possible mapping, from each of the outcomes. So that's what this mapping is doing. Okay, and so this range of possible values that we get when we map the set S to the real number system, right? So that's what this random variable x is. This set of numbers is going to be called S sub x, which is the support of x. We'll call this the support of x. And what the support of x is actually referring to is those possible numbers that we are mapping each of the possible outcomes to. This is the support of x. So these are the range of possible values we can get all the way to infinity. There's a range of possible values we can get in this experiment, right? We may have to toss the coin once to get a heads, twice, and so on. So this is called the support of x, right? Of the random variable x. Okay, right. So this support of x, all the range of possible values that we can have, and I've included 0 here as well for the trivial case where you don't do any experiment at all, right? So for this support of x, we are going to now associate each of these possible values in the support of x with some probability. Right? With some probability, you will get a heads in the very first time that you run the experiment, and with some other probability, you will get a heads in the second coin toss, and so on. Right? So for each of these possible values in the support of x, we're going to have some probability associated with it. And in this particular case, where we have a discrete possible outcome, we are going to associate each of these possible values in the support of x with some number between 0 and 1. That is the probability that we're talking about here. Okay. All right. So what we have here in this random variable is for every element in the support of x, we're going to have a probability associated with every possible outcome. And that function that determines this mapping is called a probability mass function when we have a discrete random variable like the one I'm describing right now. Okay. Now, when later on I'll show you an example of a continuous random variable, and the continuous random variable will have not a probability mass function but a probability density function associated with it. So I have a typo here. I've written probability distribution function. I meant to write probability density function here. Okay. All right. So for discrete random variables, we're going to have a probability mass function, which I'm calling p of x here. And for continuous random variables, which I'm about to introduce, we won't have a probability mass function, but a probability density function associated with every possible outcome. Now, this probability mass function in the discrete case is the probability mass function in the discrete case will be basically giving us for every possible value x in the support of x, right? It will be giving us some probability of observing that value x. So we're going to write it like this. Okay, right. So why is this interesting? That's interesting for us because we can now use this probability mass function to compute a very related kind of function called a cumulative distribution function. The cumulative distribution function is going to tell us the cumulative probability of observing some value, let's call it a, or something less than that. So to make things concrete, think about again the example that I've been giving you. The support of x is these numbers, right? 0, 1, 2, 3, 4, and so on. And each of these possible values has some probability associated with it. Call it the probability of observing 0 heads is, let's say, p1. The probability of observing 1 heads, having to toss the coin once to get a heads, is p2. Similarly, it's p3 for 2 and p4 for 3 and p5, let's say, for 4. Okay, so these are different probabilities of having to toss the coins x number of times till you get a heads. But you can now ask a question like, what is the probability of observing 0 or 1 heads? What's the probability of having to toss the coin 0 or 1 times, or 0, 1 or 2 times, or 0, 1 or 2 or 3 times until you get a heads, right? So you can ask about cumulative probabilities. So if I want to know, for example, the probability of having to toss the coin 3 or less times till I get a heads, all I have to do is I have to sum up these probabilities, right? That's what gives me this. It gives me p1 plus p2 plus p3 plus p4 will give me the cumulative probability of observing 3, of having to toss the coin 3 or less times till to get a heads, right? So this is a very useful quantity, right? This cumulative probability. And what I've just written here can be written in abbreviated mathematical form by writing a big summation symbol and writing probability of all values x where the x's are less than or equal to some number a. In this case, the example I'm giving you here is the number a is this 3. So the probability of observing all possible x's that are less than or equal to 3, right, is the summing up of these probabilities. So that's what this cumulative distribution function gives us, and you can see the connection between this cumulative distribution function and the probability mass function in the discrete random variable. Okay, so to now give you a very simple example, another simple example of a discrete random variable, I want you to think about this very commonly used example um, in data analysis. In psycholinguistics, we'll encounter this a lot in our real data sets, the binomial random variable. So this is a situation where we are doing the equivalent of tossing a coin n times. So imagine that you toss a coin 10 times, and imagine that there are only two possible outcomes, success and failure, and the probability of getting a heads, so the probability of success is some number theta, so it's a number between 0 and 1, and therefore the probability of failure of not getting a heads is 1 minus theta, right? Okay, so in this particular case, we have a situation where we can get a success or a failure every time you toss a coin. And if we toss the coin 10 times, we can get either 0 heads, all tails, right? Or we can get 1 heads, or 2 heads, or 3 heads, and all the way to 10 heads, right? These are the 11 possible outcomes that we can have. That's the support of X here, okay? All the possible outcomes. And so we can use the probability mass function for the binomial random variable to figure out the probability of observing X successes out of n trials. It just turns out that the probability mass function in the binomial is defined by this function here, right? So this function says if you have n trials, the probability of getting X successes can be computed by multiplying the term n choose X, right? N choose X is just the number of ways in which you can choose X from n trials, right? So what this means is that if I have 10 trials, how many ways can I get 1 heads, right? If I have 10 trials, I could get heads in the very first trial and then tails for all the other cases, all the other 9 cases. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is one way that I can get a single heads. Here's another way that I can get a single heads, right? So you can imagine that there are different ways in which you can get 1 heads. So n choose X tells you how many different ways there are to get X successes in n trials, okay? So this binomial random variables probability mass function P of X is going to tell us the probability of each of those possible X's once we decide on a theta value, so the probability of success, and once we decide on the different on the sample size, right? So if I say that my sample size is 10, if I'm running 10 experiments, I'm going to toss the coin 10 times, I can ask a question like, what's the probability of observing 1 heads, okay? And this I can do easily now because I know the function in equation 4. N is equal to 10, so I'm going to write 10 choose 1, right? And then I'm going to write, let's say my probability theta of success is 0.5. I'm just going to use that as an example, okay? So 0.5 is my theta. So X is 1, so this is going to be 0.5 to the power of 1. And looking at the equation 4, sorry, I should have written 0.5 here. Let me see if I can undo this now. Okay, so I can erase all this, I think, and redo this properly, right? Right, so I've written 10 choose 1 here, 0.5 to the power of 1, and 1 minus 0.5, which is 0.5 to the power of 9. Okay, that's what this equation tells me to write. So this allows me to compute the probability of getting exactly 1 heads when I'm tossing a coin 10 times. Okay, that is the whole point of defining a probability mass function associated with a binomial random variable. It allows us to compute the probabilities of every possible outcome. Okay, right. What's going on? Why is this not working? Can I move to my next slide in this mechanical way? Yes. All right. So as I just said, imagine that we have 10 coin tosses and the probability of success is 0.5. We can ask this kind of question: what is the probability of getting 0 heads, 1 heads, 2 heads, using the equation 4 that I showed you earlier. But we can also compute the probability of computing getting 0 or less heads, 1 or less heads, 2 or less heads. This cumulative probability can be computed by using the cumulative distribution function associated with the random variable. Okay, so let's do this ourselves. Okay, in R, there's a function associated with the binomial random variable called pbinom, which computes this cumulative probability for you. Okay, so that's what I'm trying to show you right now. All right, so let's try this. Okay, we're going to use, what we are doing now is we're going to compute the cumulative distribution function using the pbinom built-in function in R. We're going to compute the cumulative probability of getting 0 or less heads, 1 or less heads, 2 or less heads, and so on. Right, so we have a sample size of 10. Probability of success, the theta that I had shown you earlier, is set at 0.5. And what I'm going to now do is I'm going to repeatedly compute 11 possible cumulative probabilities. So I'm going from 0 to 10 for the variable x, and each time I'm going to use the pbinom function for each of those x values going from 0 to 10. And for sample size 10 and probability 0.5, I'm going to compute using pbinom the cumulative probability. Remember, the cumulative probability of observing some number a or less than that, where a can be 0, 1, and all the way to 10. Okay, so that's this cumulative probability that I can compute, and this is the cumulative distribution function of the binomial random variable. And so that's what I've done here. Okay, so what I've done is that I'm computing this cumulative probability that I just showed you, right? So earlier I had written probability of x less than or equal to a, but now I'm writing probability less than or equal to x. This is just a variable. I can write whatever I like here, you know. This is just a convention that I was using for referring to one of these numbers between 0 and 10. Okay, so don't get confused by the way I use my variables. Anyway, so now what you're seeing is that on this last column here, you're seeing the cumulative probability of observing 0 or less heads, 1 or less heads, 2 or less heads, and so on. And in fact, this computation is not exactly correct because it's rounded to 2 digits. Let me now do this by hand to show you what the actual number will be. Okay, so let me open an empty thing here. So what I want to do is I want to compute choose 10 choose 1, or 10 choose 0, sorry, is what I was going to compute for you. And I'm going to say that my probability of success is 0.5, and I have 0 here, and I'm just writing down equation 4, okay, by hand right now. And so what I've done now, is that what I've done here is that I have computed the probability of observing 0 heads. Okay, and that's this number here. So if you go back now to my where is it? Yeah, here, right? If you go back to my my table here, this number is actually not exactly 0, but it is that small number near 0, right? So what I'm doing now is that I'm going to be, if I ask what's the probability of observing 1 or less heads, I'm going to have to sum up the probability of observing 0 heads and the probability of observing 1 heads, right? So this is actually a cumulative probability. It's the sum of those two possible outcomes. Similarly, the probability of observing 2 or less heads is going to be the sum of observing probability of observing 2 heads plus the probability of observing 1 heads and 0 heads, right? So that's what this cumulative distribution function gives you. What is this useful for? Why am I telling you about this? The reason I'm telling you about this is that we will often encounter random variables where we will want to answer questions like these. What is the probability of observing something between 4 and 6 heads? That is a question that we will ask when we have real data, because that is how we will try to decide what is true about the world. Okay, so that's why it's important to understand the underlying machinery of a random variable. You can also visualize the cumulative distribution function. So what you're seeing here is difficult to see because of my the limitations of my figure, but on the x-axis what I have is the values ranging from 0 to 10, and on the y-axis I have the cumulative probabilities, right, of all possible outcomes or something less than that, right? So this one here is the probability of observing 10 or less heads, right? And you can see that it has to be 1 because it encompasses all possible outcomes, right? So this is a characteristic shape that you will see in cumulative distribution functions. Notice that this cumulative distribution function is discrete in the sense that there is nothing between the dots, right? You can have 0 heads, you can have 1 heads, you can have 2 heads, but you can't have 1.5 heads in a 10 coin toss, right? And that's why I don't have a connected line here. I've got disconnected dots here because it's a discrete distribution, okay, with discrete possible outcomes. All right. So the probability mass function that I had shown you earlier in equation 4, this is able to tell us the probability of getting exactly x successes, right? If I want to know what's the probability of getting 1 head, I can use my equation 4 to figure that out, right? So we can also get this answer, the probability, we can do these calculations for specific possible outcomes using the cumulative distribution function, right? This should be obvious, right? So because if I now want to know what's the probability of observing exactly 6 heads, and I have all this cumulative distribution function table in front of me, all I have to do is take the difference in these two probabilities, and because this probability is telling me the probability of 5 or less heads, and this probability is telling me the probability of observing 6 or less heads. So if I take the difference between those two things, I will get the probability of observing x equal to 6 heads, right? So I can use the p-binom function to figure out these kinds of details, right? So if I want to know the probability of observing exactly 1 heads, I can use this command that I've shown you here to compute that probability, right? And just to make sure that this number is correct, I have also done this calculation by hand, right, using R, and you can see that the numbers match up. These two numbers match up, right? So what I'm showing you here is that the cumulative distribution function and the probability mass function, they're two sides of the same coin. You can use one or the other to answer both questions. Questions being, what is the probability of one possible outcome x appearing, or what is the probability of observing x or less than that x, or some outcome like x or something less than that. Okay, all right. So in the binomial case, this equation that I've been writing out by hand in R, this actually has, this is the PMF, right? This is the probability mass function. In R, there's a function called D binom, right? D for D is a very confusing word now here, because D stands for density here, right? So this D binom function allows you to calculate the probability mass function of the binomial random variable, right? So if you want to know the probability of observing exactly 1 heads in 10 coin tosses, you can do that with this command here that you're seeing here. Okay, all right. I will explain in a minute why this probability mass function is called a D binom function. Okay, I'll just explain that in a moment. But what I'm showing you now is I'm using the D binom function to plot all the possible outcomes in this random variable, where I'm assuming that the probability of success is 0.5. What I'm showing you here is for all possible outcomes going from 0 to 10, what is the probability of each of those outcomes, and I computed those using the D binom function. Okay, So that's what these functions, the d binom and p binom functions do. They allow you to compute the probabilities of possible outcomes or the cumulative probabilities of some possible outcomes. Okay. All right, so to summarize, when we have a discrete random variable like the binomial, right, the definition of this random variable is important to keep in mind, because in the real world, when you encounter real data that is coming from a binomial random variable, underlyingly it will have all these machinery behind it that we'll be using for doing the statistical analyses, right? So it's important to keep this in mind. What is the underlying what are the underlying components of a random variable such as the binomial random variable? Okay, so basically this binomial random variable will be mapping every possible outcome s to some real number value, which is called the support of x, and each of these elements in the support of x will have associated with it some probability, which we can compute from the probability mass function, right? And we can also compute cumulative probabilities using the cumulative distribution function. Okay, so that's the story with the discrete case. We can also generate random data now, okay, from this random variable, the binomial random variable. There is a function called rbinom in R standing for random, which allows you to generate binomial data, simulated data. We will be using this a lot later on when we are simulating experiments. Okay, so I can simulate a coin toss done 10 times, put n equal to 10, and I'm specifying here just as an example that the probability of success is 0.5. And so what I produce in this experiment is a range of possible outcomes. You got a sequence of zeros and ones. Zeros are tails and ones are successes. So that's the mapping, right? In the support of x, that's the mapping that you can get between possible outcomes. Okay. All right. So what we have learned so far is that we have, for the binomial random variable, we have the d binom function, which gives us the PMF, probability mass function. We have the p binom function, which gives us the cumulative distribution function of the random variable, and we can generate random data with the r binom function. Okay, so these are three important tools that we have for understanding the binomial random variable. Okay, we will need this later on. Now I want to turn to the continuous case. You can also have situations where your data are not coming from a binomial distribution, but they're coming from some random variable that's generating continuous data. So an example would be reading times, right? You don't have zeros, ones coming out of reading times, but you got 500 milliseconds, 525 milliseconds as possible, reading times that you're getting from your experiment. And this is a continuous value because between 500 and 525 milliseconds, there's an infinity of possible values that you could have in principle. Okay. So an example of a continuous random variable is something that we call the normal random variable. I'm sure you've encountered this before. This is a characteristic shape that you see in the normal distribution. This function that you're seeing here is describing the density associated with every possible outcome in a normal random variable. Okay, so this density is called the probability density function of the normal distribution. And what goes into this function is any of the possible values in the support of x, and once you plug in that value x, assuming that mu and sigma are pre-specified, right, you decide on some value for mu and sigma, you will get a number out of this, and that number is going to tell you the shape of this distribution here. So on the x-axis you have all the possible values of x, your reading times, for example, in an experiment, and this function is going to tell you the shape of this probability density function. Okay, so we need to understand this a little bit in order to proceed. In R, this function, this curve that you're seeing here, will be drawn by using something called the d norm function, right? And so now you can see why the word d turns up in the binomial distribution, d binom. And right now I'm using the d norm. I'm talking about the d norm function, right? So what's happening here is that for uniformity, probably the developers of R, they decided to call this class of function with the same name, right? So the probability mass function in the discrete case is named the dbinom function, and the probability density function in the continuous case is called the dnorm function. So they're using the letter D to stand for this uniform probability mass or probability density function in the binomial, in the discrete and the continuous case. What you have to understand is that in the discrete case, we don't usually call this function a probability density function, but in R we will definitely write dbinom, even though what this refers to underlyingly is a probability mass function. Okay, so you have to remember, if you go back to the discrete random variable, what's distinctive about the discrete random variable is that we have discrete possible outcomes. And because these are discrete possible outcomes, we can talk about the probability of each of these outcomes. In the continuous case, it's a different situation, right? When you have a continuous random variable like reading times, okay? So let me just draw a little bit here. So let's say I have a continuous random variable like reading times, and so I have as possible values that I can observe in an experiment. I have 200 milliseconds, 250 milliseconds, 300 milliseconds, and so on, right? These are possible values. Now it just turns out that when I define the probability density function that is associated with each of these possible values, I will draw something like this. Okay, so on the x-axis are the possible values, let's say from 200 to 300, let's say. Of course, these could be larger or smaller. So I can draw a normal distribution like this that describes the more or less plausible values that I can observe in the data, right? So what this curve is actually telling me is that this range of values is more likely to occur than these extreme values on the tails. That's what this probability density function is giving me. Importantly, what this probability density function does not give me is the probability of observing exactly the number 300, let's say. So suppose I want to know what's the probability of observing a reading time like 300 milliseconds. Remember that in the discrete case, I could ask a question like this. So in the discrete case, right, in the discrete binomial case, I was asking questions like, what's the probability of observing 3 heads? This question I can answer if I have 10 trials. Oh, sorry. How do I get rid of this now? Okay, so if I have 10 trials and I want to know the probability of observing exactly 3 heads, and I assume that the probability of success is 0.5, I can compute this exactly. Sorry, 0.57. Okay, so I can compute this probability exactly in the discrete case. I can't do that in the continuous case. Why? The reason is that we will define probability in the continuous case as the area under the curve. Right, this is a continuous curve here now. Remember that in the discrete case, the probability mass function was not continuous. If you have 0 to 10, I had drawn these dots for a reason and did not connect them. Right, I didn't connect them, and there's a reason for that, because I can't have any value between this one and this one. In the continuous case, there will be an infinity of values between, let's say, 250 or whatever this number is. Between these two values, there will be an infinity of possible values. So that's why I've got a continuous curve here. So in the continuous case, we cannot talk about the probability of a point value. Why? Because probability is defined as the area under the curve, and the area under the curve for a point value is always going to be 0. So the probability of observing exactly one particular number in a continuous distribution will always be 0. You don't need to do any calculation for that. However, in the continuous case, you can ask questions like, what is the probability of observing a value between 300 and let's say 250, right? This probability can be computed using a cumulative distribution function. That's why it's useful. And it can be computed by calculating the area under the curve here, right? So we need to actually do some calculations to find out the area under the curve to figure out these kinds of probabilities. Okay, so I got a little sidetracked here, but what I was trying to get at was that we have a probability density function associated with a continuous random variable, which has properties that are very different from the probability mass function in a discrete random variable. Okay, and the key issue here is that you cannot ask questions like, what's the probability of observing some exact number, some point value, right, in the support of this continuous random variable, because the answer will always be 0, right? And what this probability density function in equation 6 is giving you is it's telling you the what's called the density of each of the possible outcomes. So what this curve, the purpose of this curve is going to be to allow you to compute the probability of observing some value between some range or the other, and we will do that by calculating the area under the curve. Okay, all right, so in the continuous random variable associated with the normal distribution, we have the dnorm function, which allows us to draw this probability density function, right, for different values of x. And having specified the mean and standard deviation, we can draw this PDF. Okay, right, so so here's an example. So what I've done here is I've drawn a normal distribution's probability density function where I'm assuming that the mean of the normal distribution is 0 and the standard deviation sigma is 1. Okay, so that's what this curve will look like, and this curve, as I said, is telling me the density of each of the possible x values here, but the purpose of this distribution will be to allow us to compute the probability of observing something between, let's say, +3 and -3, and we will do that by computing the area under the curve. Okay, that's going to be the relevance of learning about the probability density function, and this is how we will use it in real life. Okay, so this is what I'm showing you here. So I'm going to typically write, whenever I want to know what's the probability of observing, let's say 1.96 or something less than that in a normal distribution with mean 0 and standard deviation 1, I will have to compute the area under the curve, which is the shaded region here. And this is how I will write that mathematically. Okay. All right. So I can also use the cumulative distribution function built in R to ask questions about the area under the curve for the normal random variable, right? So I can now ask a question like, if I have a normal random variable with some mean and some standard deviation, notice that the x values can range from -infinity to +infinity, right? They can go up to infinity in either direction. Okay, so because this probability density function is supposed to represent the area under the curve, is supposed to represent the probability of all the probabilities of all possible outcomes, what is the probability of observing any possible value from -infinity to +infinity? That's going to be the area under this curve, and that because this is a probability distribution, that area under the curve has to sum to 1. Okay, and so we can check that now. So let's check this, right? So what I'm doing is I'm using the cumulative distribution function built into R to ask what's the area between +infinity and -infinity. It's kind of a ridiculous thing to do, okay, but I'm just doing it for fun. So what I'm trying to show you is that the area under the curve between +infinity and -infinity is 1, right? That's what I just computed with this. Similarly, I mean, now I can ask a more sensible question. What is the what is the probability of observing something between +2 and -2? I can ask that question using the cumulative distribution function, right? I compute the cumulative probability of observing everything below 2 and subtract from that the probability of observing anything less than -2. Okay, and that gives me the probability of observing values between 2 and -2. This is why we need to understand what a cumulative distribution function is, because we need to answer this kind of question very often when we are doing data analysis. Okay, so this is why I'm teaching you all this. We can ask other questions too, like what's the probability of observing values between 1 and -1? You can see that the answer is 68%, and so on. Okay, all right. So you can also ask another very interesting question now. And that interesting question is, if you have some normal distribution, okay, so let's say I have some normal distribution like this, and what you want to know is, what is the value on the x-axis, which I'm going to call a quantile, okay, I'm going to call it Q. What is the value on the x-axis such that the area to the left of it is 95%? So what I need to do is I need to find this Q such that this area under the curve going all the way to -infinity sums up to 0.95. Okay, so it turns out that in R they provide you with a function for figuring out what that Q is, and that function is called Q norm, right? And what this takes as input is the probability that you want. So this probability here, so I said 95% here, but in the example I have 97.5%. And for a given normal distribution with some mean and some standard deviation, I just chose some arbitrary examples. This tells you the quantile such that the area to the left of it is 97.5%. This is a super useful thing to have as a tool when you want to find a particular quantile, a cutoff point in a normal distribution. Okay, and this Q family of functions will be available in every distribution that you have in R, the binomial and other ones as well. Okay, so I know that all this stuff that I'm talking about seems very abstract right now. You must have encountered it earlier, but you don't really see the relevance of it yet, but it will soon become highly relevant when we start analyzing data. Okay, so it's important to understand the underlying structure of a random variable when we are actually analyzing data, and the underlying structure crucially involves the probability mass function or the probability density function, depending on whether it's discrete or continuous, on the cumulative distribution function, and this Q norm function is a useful function for computing the quantile given some probability. Okay, so these are very useful tools for statistical inference and for understanding what the probability of what a random variable is. Okay, so one special kind of random variable that sometimes turns up in statistics is the standard or unit normal random variable. This is the normal distribution with mean equal to 0 and standard deviation equal to 1. Right? This is called the unit or standard normal random variable. Right? This random variable is actually quite interesting, so it's worth thinking about for a second. So if you have one fact that you need to know is the following. So here's a fact that you need to know. The fact is that if you have a normal random variable with some mean mu and some standard deviation sigma, okay, you can transform this random variable to a new one, which I'll call z, okay, by taking x minus mu and dividing by sigma, and this random variable now will be a standard normal random variable. That's the one that I just showed you. Okay, this one here. So that's what I've shown you here, that you can transform any normal random variable to a standard normal random variable. Okay, and that transformation is given here. This will become relevant very soon when we start talking about t-tests and so on. Okay. All right, so in the case of this standard or unit normal random variable, we can just use this p-norm function to compute things like the cumulative probability of observing 2 or something less than that, right? So what this p-norm function is actually saying underlyingly when I write pnorm 2, what I'm actually saying is that I want you to compute the um, the area under the curve. So compute the probability of observing 2 or something less than that in a standard normal random variable. So these are the default values in the pnorm function, and that's why I haven't written them here, right? Because it's understood that the default values will apply if I don't specify them. If I was calculating the area under the curve for some other normal distribution with some mean other than 0 and some standard deviation other than 0, then I would have to specify the actual values here, and then I would get my this probability of observing 2 or something less than that. Okay. All right, we can I think I can ignore this right now and move on. So now notice that if I have a standard normal random variable and I ask a question like what is the probability of observing 2 or something less than that, that's this area under the curve here, right? But I also told you earlier that the total area under the curve is 1, right? Therefore, if I've asked a question like what's the probability of observing something like 2 or something less than that, and that's this area under the curve, I can also use this to calculate the probability of observing some value greater than 2, right? I could do that by simply computing this value. I'll call it P, and doing 1 minus P, because 1 is the total area under the curve, so I can compute 1 minus P to figure out this area under the curve, right? So that's what I'm showing you here, that we can exploit the fact that the total area under the curve is 1 to figure out, once we know one side of the area under the curve, we can figure out the other side. Okay. There's another trick for doing this calculation. So the calculation I'm talking about is if I want to know what's the probability of observing some number like 2 or something greater than that. Okay, if I want to calculate this area on the curve, one way to do this is the way I just showed you, by subtracting from 1. But another way to do this is to set this parameter to lower tail equal to false. What that does is it calculates the area under the curve to the right of the number instead of the left of the number. That's what it means to have lower tail equal to false. That means the upper tail is what is being computed. Okay, so these are different ways to compute the area under the curve in the case of the normal distribution. Okay, so to summarize, in the normal distribution we have these 3 built-in functions, dnorm, pnorm, and qnorm. These allow us to compute various quantities, as I showed you, and we have this analogous functions in the binomial distribution and other distributions. Okay, so we'll be using these a lot later on. All right, so that was the quick introduction to probability distributions and to random variable theory. I want to now turn to the next important topic, which is maximum likelihood estimation. So in practice, what we do with maximum likelihood estimation is that when we have some data, let's say I have some continuous data, I'll call this x1, x2, x3, x4, let's say I have 4 data points, right? Typically what I will do is I will calculate the sample mean, which I'm calling x bar, and the sample standard deviation, right? So these quantities, right, are called maximum likelihood estimates, right, of the true underlying parameters which we don't know, right? So typically when I'm doing some data collection, I'm going to assume that the data are coming from some random variable, and so let's say I assume that the random variable is a normal continuous random variable and it has some unknown mu and sigma. These are the parameters in the probability density function. I don't know what these are, right? These are unknown to me. I'm going to estimate these parameters, right? So the true parameters are mu and sigma. I'm going to estimate them using the maximum likelihood estimate x bar for the mean and the standard deviation estimate for sigma, right? So these are estimates from the data of these true unknown values. So I wanted to understand why they are called maximum likelihood estimates. Okay, that's what I'm trying to explain now. So to explain this, I'm going to now take again the example of a binomial distribution. So assume that I toss a coin 10 times, and I'm going to count the number of heads that I get each time. Okay, I'm going to repeat this experiment 5 times in all. Okay, so that means I've done a total of 50 coin tosses, and each time I toss the coin 10 times, I'm going to count the number of heads that I got. So I can use the R binomial function to do this, and as a result of this calculation, I see some random outcomes. If I ran this again, I would get different numbers each time. So what I've got here is some result of some 5 experiments that I did. I've got 5, 4, 3, 5, 2 heads, right? Now I can ask for each of these experiments, what's the probability of observing 5 heads? And I can ask what's the probability of observing 4 heads, right? And the probability of observing 3 heads, and bear with me for a minute, 5 heads, and probability of observing 2 heads, right? So these are 5 experiments I did. Each of these can be assumed to be completely independent of each other, right? So if I toss a coin 10 times, I count the number of heads, I do that again, that's, fair to assume that this is an independent experiment, okay? Although, of course, it's me doing the experiment again and again, so there's some commonality there, and if somebody else did the experiment, they might do the coin tossing slightly differently. Those are small technical details. We will ignore those right now and pretend that each of the 5 experiments are independent, okay? All right, so I have five outcomes, and I can calculate the joint probability of observing this sequence of heads, right? 5, 4, 3, 5, 2. And because each of these are independent events, I can just multiply these probabilities out, right? So the joint probability of observing, right? I'll write it like this. The probability of observing 5, 4, 3, 5, 2. This is the joint probability of these outcomes. This can be computed by multiplying out all the probabilities of these possible outcomes, right? Using the binomial mass function, that the probability mass function I'd shown you earlier. So that's what I mean by the joint probability of getting all these values, and we can compute these now. Now the interesting thing is that whenever I compute, for example, this probability 5, I'm going to compute it like this. I'm going to have to compute this quantity here, theta 5 and 1 minus theta 5, right? So this probability is going to depend on the value of theta now. So the joint probability, the product of all these probabilities, is going to actually depend on one variable now, which is theta, right? So it becomes a function of theta. And so that's what we are going to now say, is that when we have all these 5 possible outcomes, which I'm writing in this very cumbersome way, okay? For the first experiment, I have the first outcome. For the second experiment, I have the second outcome. This is very convenient mathematically, but it's somewhat of a pain to write right now. So I have 5 experiments, and I have 5 possible outcomes, right? Here, right? And so what I'm doing here is that I'm going to have to multiply out each of those probability mass functions for each of those possible values, and these will all be a function of theta now, because that's the only variable in the probability mass function that is not specified. And that's why we call this joint probability, we call it a likelihood function, and it's a function of theta, right? So we'll write it like this sometimes, okay? And so what this means is that if I plug in different values of theta each time in that product that I computed, I'm going to get a different number each time, right? I can plot that curve, okay? So let's do that. That's an interesting thing to do now. So to give you a handle on what's going on here is that what I'm doing here now is that I've got all my x's. Remember what my x's were. Let's go back here. X is all these possible outcomes here, right? 5 numbers here, right? So what I'm doing is I'm taking that vector of x's for an experiment of size n, and I'm computing using d binom. I'm computing the probability density probability mass function, of each of those possible values, and I'm using the prod function to multiply those probabilities out. So I'm literally doing what I showed you in this circled part here, okay? I'm calculating all those probabilities here, and the number that I get is this one here, but this number actually depends on my deciding that theta is 0.5. Suppose I decided that theta is 0.1, then I would get a different number for the same calculation, right? So that's what I'm saying, that the likelihood function is now simply a function of theta, and theta can range from 0 to 1 because it's a probability. Okay. All right. So what we can now do is we can actually compute the likelihood function for different possible values of theta ranging from 0 to 1. So let's do that, right? So what I've done in this piece of code here is for values ranging from 0 to 1 by a step size of 0.01, I'm going to compute I'm going to compute the product of those binomials that I just did for each possible value of theta. Okay, and what that gives me is a smooth function ranging from 0 to 1 that tells me the different values of the likelihood function. This, what I'm drawing here, is the likelihood function L of theta, right? Telling me the different values of the likelihood function for different values of theta that I could have. And what's interesting here is that there is one possible value, one particular value here on the x-axis of theta that gives us that maximum value on this curve. And that maximum value, this is the maximum point on this curve, right? And this is the value that corresponds to that point. This value that gives us the maximum point on the curve is called the maximum likelihood estimate. That's why it's called the maximum likelihood estimate. Okay. So in the case of the binomial, you can analytically work out that this maximum point, given some data, right? So what was our data? Let me just remind you quickly. It was 5, 4, 3, 5, 2 heads, right? That's our data right now. So given the data 5, 4, what is it? 3, what did I already forgot the numbers, sorry. 5, 4, 3, 5, 2, right? Yeah. So 5, 4, 3, 5, 2 was our data. Given these data, there's a formula for figuring out what is the value of theta that is the most likely value given this data, right? So you will see often, you must have learned this also, that the proportion of successes that you get, right, given all the data that you have, can be used as an estimate of the true value of theta, and it's the maximum likelihood estimate, right? It's telling you, given the data, what is the point, what is the theta value such that it would have the maximum that would represent the maximum point on this likelihood function. Okay, so what is this formula that I'm showing you here? X is the number of successes and n is the sample size. So right, if you do an experiment with 10 trials and you get x equal to 5, your maximum likelihood estimate of theta, which I'm going to write as theta hat, is 5 over 10, which is 0.5. 0.5 is going to be the maximum value in the likelihood function for that particular experiment. Okay, now this result seems very magical. I mean, just from some data you can get the maximum point in your likelihood function, but it can be proven analytically. It's a very simple analytical proof. It's provided in my lecture notes, in the linear modeling lecture notes, which I don't expect you to read. You can just trust me on this fact that this is the maximum likelihood estimate. But if you're curious, you can see the derivation. It requires some calculus. That's why I'm not discussing it in this course. Okay. All right. So this was the discrete case that I just discussed. In the continuous case, for example, the normal distribution, you will have a similar situation. The sample mean will give you the maximum likelihood estimate for mu, and the sample variance will give you the maximum likelihood estimate for the unknown true variance. Okay. All right. So the important thing to understand here is that the maximum likelihood estimate allows us to get an estimate of the true unknown parameters. In the case of the binomial, it was the parameter theta, the probability of success. In the case of the binomial, in the case of the normal distribution, it's the mean and the variance of the normal distribution. So we can get estimates of these from our particular data that we have collected, right? So that's the relevance of these maximum likelihood estimates. They give us some estimates of the true parameters, not necessarily the correct estimate, but they give us the maximum likelihood estimate given the particular data that we have. Okay, so this now leads us to the distributional properties of this maximum likelihood estimate under repeated sampling. That's where the statistical analysis becomes possible, right? When we start thinking about possible repeated experiments and calculations of the maximum likelihood estimate under repeated experiments. So that's something I will discuss in the next lecture.